All right, welcome to the video lecture on section 15.5, which is about surface area. So here's the scenario. We're going to have some function. Z is a function of x and y over some region D. That might be the natural domain of the function, but very often we'll be restricting the domain to look at just part of the graph of this. And I know that when I graph a function like this, I'm getting a surface in 3 space. So it's a two-dimensional object, but it's living in 3 space. Now if I just integrate f of xy, I'm calculating the signed volume that's between that surface and the xy plane. Today we're switching our attention to just looking at the surface and trying to figure out the two-dimensional area of that surface. So as we attempt to do this, we're going to go through our usual 4-step process. We are going to chop. So we're going to chop this up into little rectangles. Now, in theory, it's not necessary to make all those rectangles the same size. In practice, it's a little bit simpler if we do. Okay. So if I have a rectangle, all of the rectangles, I'm going to have their dimensions be delta x and delta y. And that way, delta A, the area of each rectangle, is just that product, delta x times delta y. And then I want to approximate. So I want to try to approximate, if I have the ijth rectangle, I'm going to just call that Rij, okay? I want to try to approximate the area of the surface that lies above that. Now to illustrate what we're doing here, I've brought a friend today to help me. So this is Penelope. She's a very lovely, very yellow mouse, okay? And her stomach here, we're going to view that as D. That's the region in the xy plane that's the domain for things. And you can see we've chopped things up into little rectangles, and in fact this rectangle right here happens to be Rij. It is the ijth rectangle. So what we're trying to do is figure out what's the area of this little patch of her fur. So this part of her is the graph of the function. Now, obviously, Penelope is a solid. She is a 3-dimensional mouse. She lives in 3 space. She tried 4 space, didn't like it, came back to 3. Okay, so you have to recognize that we're just talking about her beautiful yellow fur here. We're not talking about her innards, then we could calculate volume. We're just talking about the area of the beautiful yellow fur. All right, so what I'm going to do to approximate that, I say, well, if I want to approximate a surface, I would usually do it with, I don't know, a tangent plane. So I'm going to pick a representative point, calculate the tangent plane at that point, and then find the area of the portion of that plane that lies above Rij. So I think just to keep things simple, I'm going to choose as my representative point the lower left-hand corner here. We'll call that Pij star. Okay, so that's the point with the smallest x and the smallest y value. So on Penelope here, if the x-axis is coming towards you and the y-axis is going left and right, that would be the point that's furthest back and furthest to the left. So that's going to be this point right here. So we're coming above there, calculating the tangent plane, and using that area to approximate things. Now, it will always be the case that what lies above a rectangle will be some sort of a parallelogram. In the example here with Penelope, she's a rather simple shape. The tangent plane, it looked like we were actually getting a rectangle. There's no guarantee that we're going to have right angles here, but we will always get some sort of a parallelogram. And that's absolutely lovely, because if we have a parallelogram, then I know that I can calculate the area of that. This is a parallelogram in 3 space. If I can find these 2 vectors, it's very exciting. If I can find these 2 vectors, which I'm just going to call A and B, if I could find those 2 vectors, then I could take their cross product, and the magnitude of that would be the area of this parallelogram, which I'm going to call Tij. So it's the area of the part of the tangent plane at this representative point that lies above the ijth rectangle. Okay, so I want to try to figure out what these vectors here are. Okay, so let's just suppose that B is the one that corresponds to the delta x here. Okay. Now, with Penelope, of course, x is what's coming forward towards you. Okay. So if I take a look at this, I actually know how far forward we're going to be going, because this is lying above this rectangle. So we're going to come forward a distance of delta x. But as we're coming forward this distance of delta x, we're not moving left or right at all. So our y isn't changing at all. So I just need to know how much z is changing. Now I know how much x is changing. I want to know how much z is changing. And I have this nifty function that tells me how fast z changes with respect to x. It's called the partial derivative with respect to x. That gives me the rate of change with respect of z with respect to x. It corresponds to the amount that z would change if we let x change by a distance of 1 unit. We're not letting x change by a distance of 1 unit, so the amount that z will change will just be delta x times f sub x pij star. So the amount that z changes is the rate of change with respect to z times the amount that x changes. By a similar argument, then A would be, and I probably should have called this one A and that one B, but it doesn't matter. Okay. A is 0 delta y times f sub y, evaluated at my representative point. Okay. So when I'm trying to find this side here, we're going to go to the right a distance of delta y, because we got to stay above this rectangle. We're not moving forward or back, so x isn't changing at all. And so any change in z is due solely to the change in y, so that we can calculate that. Excellent. Now this means that we can calculate what Tij is. Because Tij is just going to be the magnitude of B cross A. Now the order here does not matter. If I cared about this as a vector, I would care what order I crossed them in, but I'm caring about the magnitude of it, so the order in which I cross them doesn't matter at all. Okay. All right, if I look at what B cross A is, that's going to be the symbolic determinant I, J, K, delta x 0, delta x f sub x at Pij star, 0 delta y times f sub y at Pij star. So I know I'm going to get some i's, some j's, and some k's. For the number of i's, it's nothing minus this product. That's going to be f sub x evaluated at Pij star times delta x delta y. For the j's, let's remember we have to subtract that. So I'm going to do this one backwards. It's going to be nothing minus this diagonal product, which is just f sub y at Pij star times delta x delta y. And then if I look at the k's, that's just delta x delta y minus nothing. Cool. So the magnitude, oh, and actually, before I calculate the magnitude, let's just notice that there's a delta x, delta y in each one of these, so I can factor that out. So this is equal to delta x, delta y times f sub x at Pij star, comma f sub y at my representative point, comma, 1. So now I can calculate the magnitude of B cross A. And I can say, since I've got a scalar multiple of a vector, it's the absolute value of that scalar. Now, delta x and delta y are both bigger than 0, so I'm going to be able to evaluate that absolute value and just remove it, times the square root of f sub x at my representative point squared, plus f sub y at my representative point squared, plus 1 squared, which is 1. Which is the square root of the partial with respect to x at my representative point squared, plus the partial with respect to y at my representative point squared, plus 1, times delta x delta y. All I did there was just evaluate the absolute value by saying what was inside was positive. All right, this video has been going for a while, so I'm going to stop here. The next video will pick up with steps 3 and 4 to finish up our formula for finding the surface area. Say goodbye, Penelope. You did real good.